Okay, so we now have an idea of what a Cauchy sequence of rational numbers is, and this is the type of sequences we are going to use to define real numbers. But this is not enough. I mean, only knowing about Cauchy sequences is not enough. There is one more issue that needs to be addressed, and that's why we have this second section, equivalent Cauchy sequences. To see what the issue is, we consider two Cauchy sequences of rational numbers. One is this sequence with which we are familiar. We have seen it at least twice by now. It is supposed to converge to the number square root of 2. We already somewhat know what square root of 2 is. It's an irrational number. It's the length of the hypotenuse of a right angle triangle, two of whose sides are of length 1. But at the same time, we can obtain another sequence from this sequence in this way. What you do, you add the number 1 to the last digit of each term. That gives you 1.5. In place of 1.41, you have 1.42, and so on. Now, just like we feel that the first sequence converges to square root of 2, you can also see that it seems like the second sequence also converges to square root of 2. Why? Because these numbers look different, but note that this is the decimal expansion of square root of 2, a few digits. Okay, a first few decimal digits have been shown here. In spite of this difference in the last digit, you can see that as you go down the sequence, both the sequences, that difference becomes smaller and smaller, in the sense that more and more digits match. Here only the first digit before the decimal point matches, which is 1. After the decimal point, both the digits in the tens place, means 10 to the power minus 1, but coefficient of that in the decimal expansion, they are different. But here we have 1.4, 1.4 same, only 1 and 2 are different. Here 1.41, 1.41. Okay, so here we have 2 decimal digits matching. Here we have 3 decimal digits matching. So eventually the situation is just like this sequence with the second sequence. So the point now comes, you see what the author has written. Informally, both of these sequences seem to converge to square root of 2. But this, of course, this statement is not rigorous because we have not defined real numbers yet. So we don't really know what this thing is, and in fact this whole discussion is informal. It is just what we feel about these things. We want to use this informal discussion to get to a more formal treatment of these things, and we also want to figure out how to use these sequences to define a real number. Now, if we are to define real numbers from the rationals as limits of Cauchy sequences, that's how we are approaching the subject. No, we are going to use Cauchy sequences of rational numbers to define real numbers. Then we have to know when two Cauchy sequences of rational numbers give the same limit. That's what we feel is happening here. These two Cauchy sequences are giving us the same limit. Now note that if you are using Cauchy sequences of rational numbers to define real numbers in this way, say you have a Cauchy sequence of rational numbers. To this Cauchy sequence you associate an object which you are calling a real number. We are not saying anything what this object is or what it we are not saying what the object is. It's some something that is associated to this Cauchy sequence of rational numbers. If you have another sequence, with this also you are associating one such object. You are calling these objects real numbers. Now if the situation is like this, where an is this sequence and bn is this sequence, then from our feeling about what is happening with these sequences, that both of them are converging to root 2, both of these real numbers should be equal to root 2, and in particular they should be equal. So that's why we are saying that we need a way of knowing when two Cauchy sequences are supposed to converge to the same limit. Because otherwise what happens, if we cannot recognize this before defining real numbers, then later we will have many different real numbers which actually will turn out to be the same, and that will create a mess. So we have to figure out a way of knowing when two Cauchy sequences are like this, that is, they seem to be converging to the same thing, without first defining the thing itself, without first defining a real number. Because if we do that, then the thing will be circular. You cannot say that these two sequences seem to converge to the same thing, because they do converge to the same thing, root 2. No, we don't have root 2 yet. Using only the sequences, you have to say that they are in that sense equivalent, that they should converge to the same thing. So we want a definition of equivalent Cauchy sequences, and to achieve this we are going to proceed just like the previous section, where we defined a Cauchy sequence in steps. That is, first we defined epsilon steadiness, then eventual epsilon steadiness, and finally a Cauchy sequence. Here also we won't define equivalent Cauchy sequences at once. We are going to define in steps. So in that direction, this is the first definition. So this is definition 5 to 1, and this is epsilon closed sequences. Let n start, we can actually start n from any integer, but let's just start it from 0. That's the way it's given in the text. B to sequences of rational numbers. And let epsilon be a positive rational number. We say that the sequence an is epsilon close. Don't confuse this with the ordinary definition of epsilon closeness, which is between two rational numbers. This is epsilon closeness between two sequences. Is epsilon close to the sequence bn if an is epsilon close to bn for all natural numbers n, that is the rational number an is epsilon close to the rational number bn. In other words, okay, a naught, a1, a2, etc. is epsilon close to this sequence if and only if this difference is less than or equal to epsilon for all natural numbers small n. Now this here is an example illustrating this concept. The two sequences one minus one, etc. and 1.1 minus 1.1, 1.1 minus 1.1, etc. are 0.1 close. Why? Because the difference between corresponding terms of these sequences, all of them are equal to 0.1. You can clearly see 1.1 minus 1 is 0.1. However, note that none of the sequences is 0.1 steady. Epsilon steadiness is a different concept. Okay, epsilon steadiness is about a single sequence, and epsilon closeness is about two different sequences being epsilon close to each other. Then naturally, after this we have the definition of eventual epsilon closeness, that is eventually epsilon close sequences. So this is definition 5.2.3. Eventually epsilon close sequences. Let an and bn Note one more thing, that the definitions we are now making, they are not about just Cauchy sequences, they are for any rational sequences. So let this and this be two sequences of rational numbers, and let epsilon be a positive rational number. We say that an is eventually epsilon close to Bn since you know about the definition of eventual epsilon steadiness, you can pretty much guess what we are going to have next in this definition. Epsilon close to Bn if there exists a natural number n such that this sequence is epsilon close to this sequence. That is, the notion of epsilon closeness applies to the sequences if you remove the first few terms. In other words, this sequence is eventually epsilon close to this sequence if and only if there exists a natural number n such that the distance between an and bn is less than or equal to epsilon for all n greater than or equal to n. No longer necessarily for all natural numbers n, but for all n greater than or equal to n. So that's eventual epsilon closeness of two sequences. And there is, okay, after this there is a remark. Again, the notions of epsilon closeness and eventual epsilon closeness are not standard in the literature. Just like the notions of epsilon steadiness and eventual epsilon steadiness are not standard. So we encountered those notions there, and they are there itself. I mean, once we have the definition of a Cauchy sequence, we don't need to use them anymore. So here also, these two notions have the same status. We are not going to use them outside of this section or chapter, outside of this section. Okay, now let's look at an example illustrating eventual epsilon closeness. The idea here is that one may get confused with epsilon steadiness, epsilon closeness, but the thing is that once you see epsilon steadiness and eventual epsilon steadiness were devised for defining Cauchy sequences. You are expected to, once you understand what a Cauchy sequence is, you are expected to forget those notions. Okay, the same will be the case here. Once we get the definition of an equivalent sequence, then that we have to remember that definition. Example 5. The two sequences (1.1, 1.01, 1.001, 1.0001, etc. and 0.9, 0.99, 0.999, 9999, etc. are not 0.1 close. Because if you take the difference of the first two terms, what do you get? The difference is 0.2, which is greater than 0.1. So the two sequences fail to be 0.1 close, but they are eventually 0.1 close. Because the sequences obtained from them by removing the first terms are 0.1 close. If you remove these two, that is, if you remove the problematic difference, then what about the other differences? Here we have the difference is 0.02, here the difference is 0.002, and all of them are less than 0.1. So if you remove these first two terms, then the remaining terms form sequences that are 0.1 close, and as such the original sequences are eventually 0.1 close. A similar argument shows that the original sequences are eventually 0.01 close also, and it goes like this and so forth. Okay, now with the help of this notion of eventual epsilon closeness, we can define equivalent sequences. The definition goes like this. Two sequences an and bn. Here also n is starting from 0. It does not matter what n starts from, but I want to be consistent with the text. Two sequences, this and this, of rational numbers are said to be equivalent if for every rational epsilon that is positive, the sequences are eventually epsilon close. If that happens, then we say that the sequences an and bn are equivalent. In other words, these are equivalent if and only if for every rational epsilon there exists a natural number n such that the difference between an and bn, numerical difference, that is the difference with absolute value, is, let's write in neat ink, this is less than or equal to epsilon for all n greater than or equal to n. If this happens, then we say that the sequences are equivalent. Okay, following this there is a remark. As with definition 518, the quantity epsilon is restricted to be a positive rational, but you can assume it to be a positive real also once we develop the real numbers rather than a positive real. However, we shall eventually see that it makes no difference. Whether we consider epsilon to be rational or real, and in this respect see exercise 6.1.10. There we will prove something which will ensure that there is no, it is inconsequential whether you take epsilon to be rational or real, whatever you are going to get will remain unchanged. Okay, from example, from definition 5 to 6, it seems that the two sequences in example 5 to 5 are equivalent. That is, the sequences 1.1, 1.01 and the other 0.9, 0.9 and that thing. Okay, and we are now going to prove this. We now prove this rigorously. First, we need to define the sequences properly. I mean, although we can understand from the first few terms what the pattern is, but we need a solid, rigorous mathematical definition of the sequences. So here is the proposition. Five to 8. Let an, where n varies from 1 and goes on, and bn be the sequences defined like this. An is defined to be equal to 1 plus 10 to the power minus n, and bn is defined to be equal to 1 minus 10 to the power minus n. You can see that these formulas will actually give you the sequences that we have seen in example 5 to 5. For example, if you put n equal to 1 here, then you will get 1.1. If you put n equal to 1 here, you will get 0.9, like that. Then an and bn are equivalent. Now, before we see the proof, there is a remark. This remark is about the consequence of this equivalence. Remark 5 to 9. This proposition in decimal notation asserts that these two real numbers are actually equal. Okay, this is also an informal remark. If you look at the sequence, this sequence which goes like this 1.1, 1.01, 1.001 and so on, you can vaguely understand the way we understood that those two sequences converge to root 2. You can understand that the first sequence converges to 1, and the second sequence also like that, you can understand converges to 1. So if we are able to show that these two sequences are equivalent now rigorously, then after having the definition of a real number, we can say that because of this equivalence, the real numbers associated to these sequences as their limits are actually equal. So that's why from the equivalence of these two sequences, you get this fact. Okay, once you of course also throw decimal notation into the mixture, into the picture, and for this C proposition B 2, 3. Okay, so this A, B, these things are in the appendix. We will have a look at them when the time comes. In the appendix, you see, in in this text analysis 1, the author has already said, and it's a fact, that we can develop real analysis without in fact needing the decimal notation at all. We are just sometimes using the decimal notation to write concrete numbers, but it was mentioned in the beginning itself, or towards the beginning, that the analysis does not actually depend on the number system or the way we are writing the numbers, whether we use decimal representation of a number or octal or binary or hexadecimal or even Roman numerals. It would not matter. The analysis you will ultimately get will be same. But since we are very familiar with decimal notation, so the author has devoted some appendices to that topic. So after going through the whole analysis 1, there are appendices, we will look at them. So it's from there that this thing is coming as a proposition. Okay, now let us look at the actual proof of equivalence of these two sequences. Let epsilon be some positive rational number. We need to show that for any such epsilon, these two sequences are eventually epsilon close. And for that, we are again going to start by referring to proposition 441, which allows us to choose a positive integer greater than a given rational number. We have already done that in the previous video. Now also we are going to do that. There we proved that the sequence 1 by n is a Cauchy sequence. In the proof of that fact, we used proposition 441. Now again we are going to use that by proposition 441. There exists a positive integer n such that n is greater than 2 divided by epsilon. If I am remembering correctly, there also we considered n to be greater than 2 by epsilon, but don't think that that is the only thing you have to always take. It depends on the situation what n you will choose. Okay, in this case it happens that the same choice also works here. Right, but then we have to do something else also. By proposition. So first of all, we need to use properties of order for rational numbers, and we need to also use, that means results from the previous chapter. We need to also use the result of an exercise here that we already solved there. So this is proposition 4310, that too it's part C, and exercise 435. Ten to the power n is greater than 2 to the power n. 2 to the power n is greater than or equal to n. Okay. Now what we have done here is this. proposition 4310 C tells us that when x and y are two rational numbers that are in an inequality relation like this, x is greater than y, like 10 and 2, then we can raise them to any positive integral power and the inequality will be just like that. That is, since 10 is greater than 2, so 10 to the power n is greater than 2 to the power n. Proposition 4310c justifies that. And this second inequality is what we proved in exercise 435. Hence, for any integer n greater than or equal to n, we have what? 2 times 10 to the power minus n is less than or equal to 2 times 10 to the power minus n. Here what we have done, we have again used this proposition 4310c to conclude this. 10 to the power n is greater than or equal to 10 to the power n. Now if you take reciprocal and multiply both sides by 2, you will get 2 divided by 10 to the power n less than or equal to 2 divided by 10 to the power n. This one is this and the right hand side is this. Why suddenly 2 times this, that you will realize now. And this is less than or equal to what? 2 divided by n. You see, 10 to the power n is greater than, we have strict inequality. Anyway, 10 to the power n is greater than n, so 2 divided by 10 to the power n is less than 2 divided by n. So this thing on the left side is this and 2 by n is here. Okay. And now you look at this inequality. If you divide both sides by n, you have 2 divided by n, and multiply both sides by epsilon, you have epsilon. So from this you get the fact that epsilon is greater than 2 divided by n. Okay, so this turns out to be less than epsilon. So for n greater than or equal to n, we have this absolute value equal to, this is 1 plus 10 to the power minus n minus 1 minus 10 to the power minus n. This is equal to 2 times 1 minus 1, they will cancel, and 2 times 10 to the power minus n. And this is less than epsilon. So we see that this numerical difference is less than epsilon for all n greater than or equal to n. Hence, the two sequences are eventually epsilon close. So, an and bn are eventually epsilon close. But the epsilon we chose was arbitrary, since this is arbitrary we conclude that the sequences an and bn are equivalent. That's what we wanted to prove, so this completes the proof. Now here the section actually ends. There are two exercises. Let's look at the exercises. Only two of them are there, so we can complete them quite quickly. The exercises involve some facts which are related to two sequences being equivalent. That is, if two sequences are equivalent and one of them is having some property, then the other one will also have that property. Not all properties, but some very important properties. You will see now. Show that if an and bn are equivalent, then are equivalent sequences of rational numbers. Then an is a Cauchy sequence. If and only if bn is a Cauchy sequence. In fact, this is how the thing should be. If the sequence that you are using to define a real number that turns out to be a Cauchy sequence, then any other equivalent sequence which we are thinking it should also converge to that same real number, it should also be a Cauchy sequence. If it is not like that, then that means our idea of using Cauchy sequences to define define real numbers is not correct. Luckily that is not the case, so things are okay. Now let us see how we can solve this. It's enough to show that if an is a Cauchy sequence, then so is bn. Okay, so assume this is a Cauchy sequence. Okay, let epsilon be any positive rational number. Then there exists an integer n1 greater than or equal to 1. This is I am going to write the condition for an being a Cauchy sequence such that the distance between the terms ai and aj is less than or equal to epsilon by 3 for all integers I and j greater than or equal to n1. It's only about the sequence an and the fact that it is Cauchy. Also, since an and bn are equivalent, there exists an integer n2 greater than or equal to 1 such that the distance between ai and bi is less than or equal to epsilon by 3 for all I greater than or equal to n2. Choose an integer n3 that is greater than the maximum of n1 and n2. Among n1 and n2, one will be maximum, n3 is, this is not m1, this is n1. n3 is greater than both n1 and n2. Then for any integers n and m greater than or equal to n3, we have let me write it in the middle, the calculation, that way it will be more prominent. The distance between bn and bm, this can be written as bn minus an plus an minus am plus am minus bm. Now you can use triangle inequality and write this to be less than or equal to bn minus an plus absolute value of an minus am plus absolute value of am minus bm. Now this absolute value is less than or equal to epsilon by 3. Why? It happens only when the suffix I is greater than or equal to n2. Here the suffix is n. N is greater than or equal to n3 and n3 is greater than n2, so n is also greater than n2. So that means this is less than or equal to epsilon by 3. This is coming from the first term. Because the sequence is Cauchy, this term is less than or equal to epsilon by 3 when the suffixes I and j are both greater than or equal to n1. Here the suffixes are n and m, and they are both greater than or equal to n3, which itself is greater than n1. So they are also greater than n1. So this second absolute value is also less than or equal to epsilon by 3, and because of a similar reason, this absolute value is also less than or equal to epsilon by 3, and that is because m is greater than or equal to n3, and as such it is greater than or equal to n2, and that's why we have absolute value of am minus bm less than or equal to epsilon by 3. So this now gives us epsilon. So what have we shown? Thus bn minus bm is less than or equal to epsilon for all n and m greater than or equal to n3. This shows that bn is a Cauchy sequence. So Cauchiness of the first sequence and equivalence of the first and the second sequence force us to conclude that the second sequence is also a Cauchy sequence. That is the content of this exercise. So here the solution ends, and there is one more. It turns out that not only Cauchiness but boundedness is also what can I say, is transferred from one sequence to any equivalent sequence. Let epsilon be a positive, so here they have given epsilon themselves. Epsilon be a positive rational number. Show that if an and bn, oh, here we don't in fact need the full condition of the two sequences being equivalent, but only epsilon, eventual epsilon closeness is enough. Are eventually epsilon close, then an is bounded if and only if bn is bounded. Okay, so to solve this one, it's enough to show that if an is bounded, then so is bn. So assume an is bounded. Then it will be bounded by some non-negative rational number. Then there exists some rational greater than or equal to 0 such that AI is less than or equal to n for all I greater than or equal to 1. That's what being bounded by m means. Okay. Since an and bn are equivalent. Oh no, sorry, they are not equivalent, they are eventually epsilon close. Are eventually epsilon close, there exists an integer n greater than or equal to 1 such that the absolute value of ai minus bi is less than or equal to epsilon for all I greater than or equal to n. Okay. Now for I greater than or equal to n, we have absolute value of bi less than or equal to absolute value of bi minus ai plus absolute value of ai. We have used the triangle inequality here. Now since I is greater than or equal to n, this thing is less than or equal to epsilon. We already know that inside the absolute value you can change sign as you wish. So ai minus bi and or bi minus ai, they will ultimately give you the same absolute value. So this is less than or equal to epsilon plus for any I actually we have this quantity to be less than or equal to n. So in particular for this type of i's also we have that inequality. So we get this. Now if our integer n happens to be equal to 1, if n is equal to 1, then this inequality is true for all I greater than or equal to 1. That means for all I, then this is less than or equal to epsilon plus n for all I greater than or equal to 1. That is this is bounded by epsilon plus m. Now assume This is the case when capital N is equal to 1, but it may not be equal to 1 also. It may be greater than 1. Now assume N is greater than 1. By what was that result? That says that bounded sequences are by lemma 5.1.14. By lemma 5.1.14, the finite sequence B1, B2, etc. up to Bn minus 1. If n is 2, then this will have only one term. But this finite sequence makes sense because n is greater than 1 now. The finite sequence is bounded by some non-negative rational number say L, that is this is less than or equal to L for all I lying between 1 and n minus 1. And already we had this inequality true for n, that is absolute value of Bi is less than or equal to epsilon plus m if I is greater than or equal to n. So L plus epsilon plus m for all I greater than or equal to 1. If I lies in this range, then this is less than or equal to L. So automatically it will be less than L plus epsilon plus m. And if I is greater than or equal to n, then this absolute value is bounded by this quantity epsilon plus m, and hence it's bounded also by this even larger quantity L plus epsilon plus m. So this acts as a rational number that bounds the whole sequence. Thus in this case Bn is bounded by L plus epsilon plus m. In any case, Bn is a bounded sequence. So equivalence of An and Bn and boundedness of An makes us conclude that Bn is also bounded. So both Cauchiness and boundedness get transferred to from a sequence to any equivalent sequence. So this completes the solution, and it completes this section also. In the next section, we will actually start using all these ideas to define real numbers from Cauchy sequences of rational numbers. So I end the video here. If you have any doubt about this, or if you find any mistake in these things, then please write in the comment section. So that will be all. This is me, Lucifer, from the mathematical room. Have a nice night.